Take a minute. I will begin with a word of prayer. Dearly Father, we thank you for this day. I thank you for the students. Just ask you to bless our work today and just help us to, again, Lord, to glorify you in what we do. In your name we pray, Lord Jesus. Amen. All right, so was this lecture 18? I've lost track. 18? So what I want to try to talk to you about today is just a little bit on what is known as a group action. It's not the sort of thing you can make money on. Well, I mean, maybe, but it's not that kind of group action. It's a far more interesting one. Let's see here. So here's the definition. Let G be a group. And let's let S be a set. All right. A multiplication of elements of S by elements of G in particular, a function, let's say star, it's a mapping from G cross S to S once more. So a function from the Cartesian product of the group and the set to the set again is called a group action. Good grief. If we've got a couple of things. Number one, we need that, and I'm going to use stars here for a little bit, just to get us started on the definition, but pretty soon after, once we get the applications, we'll drop the stars, kind of like in the beginning with the group multiplication. We haven't written a star in a while, right? But I think it's helpful to use the notation to start with. So the first thing is associativity. So we have to have that A but it's not quite associativity, all right? It's like associativity, but here's how it goes. A star B star X, all right, is equal to AB star X. For all AB in the group and X in the set. Before I go on, let me just emphasize what's going on here. I'm using juxtaposition to denote the multiplication in the group, and I'm using the star to denote the group action, right? So this right here is a group multiplication, right? In contrast, the stars, of course, are group actions, right? This is an abstract concept. I'm going to give you examples of group actions here once I get the definition out of our way. And then the second thing is that, E star X is equal to X for all X in S, where E is the group identity. All right. See, this mug proves my worth. As you can see, your job doesn't change lives. You do. It's me. Although, let's see here. Example one. Where are we? It is clear. Where am I? Yes. I did not know that was the Montview Student Union. Because they took out the Flames Cash thing downstairs, and I'm like, oh man, I can't put money on my Flames card without going over to Reber Thomas or whatever. I don't want to walk over there. Like, where's this Montview Student Union? I had no idea. I'm an idiot. Let's see here. So, Reber Thomas, what is it? Is it the Rot? Oh yeah. I don't know. That place I don't eat. Let's see here. His first example here, and by the way, I am just thieving, just outright stealing from this wonderful book, Abstract Algebra, 3rd edition by Beachy and Blair, which is, it's a pretty good book. This is the book I copied the wrong homework problem down from. The book is not wrong, it's my copying ability. Sorry about that. For this reason, there was no help session yesterday because everything we did was garbage. So I'm just threw it away. Sorry for those who came. Sorry, I'll get with it. Example 1. It is clear any group of permutations on the set S determines a group action. Any group of permutations on a set S determines a group action. So let me just write out. That's nice words. Let me just few more symbols there. How's that go? Well, remember what is the permutations on S? I mean, we could use this as a notation. Permutations on S. What was that? It's just sigma that goes from S to S, right? What would you need? Sigma what? Bijection, right? That was it. Those are permutations. This is saying any group of permutations. So I suppose we could look at G, a subset of these, right? A subgroup, rather, of the permutation group, right? So you have a subgroup of permutations. How does that define it? I mean, what's the definition for the action? So let's say if sigma and, sigma 1 and sigma 2 are in G, right? Well, I guess first of all, let me just define how does it work on just one. So if sigma is a permutation, a particular subgroup of the permutations on S, how would we define the group action? How do we do it? What's sigma star X defined to be? I mean, all he writes in this book is that it's clear that any group of permutation defines an action on a set S. Why does he say that? Make it clear for us. Let's finish his thought. What should I do? I need something that's in S, right? So all you do is just sigma of S, right? Of X, rather. This, of course, is an element of S, right? So I can define the group action simply by evaluation of the permutation on the set. And that definitely gives me a way to take a pair, a permutation, an element, and give me back an element again, right? Does it satisfy the group axioms? Well, one of the things we have, I'll do 2 first. Sigma equal to, we usually use the notation, let me just say the identity mapping on S, right? That's the group identity in the permutation group, right? And it's, well, you can see that. I mean, if I take the identity on S star X, that's the identity on S of X, which is equal to X again, right, for all X. So the group identity works like we'd like. And how about the associativity? It's not associativity, but it's kind of associativity. I mean, it's, what do you want to call this? We could put it into words, right? If you act by the group by one element and then act by a second element, it's the same as if you multiply the elements and act, right? So, but 1 is easy enough to verify. If we have sigma 1 star sigma 2 star X, in other words like this, right? Well, that's equal to sigma 1 star sigma 2 of X by my definition, right? which then by definition is sigma 1 of sigma 2 of x, right? But what's that? That's sigma 1 composed with sigma 2 of x by definition of function composition, which then is, of course, sigma 1 composed with sigma 2 parentheses star x. And there you have it. There's condition 1. It's a group action, all right? So any group of permutations, I would say subgroup of permutations of a set, determines an action, all right? Another example. Example 2, if H is a subgroup of G, right, then H x on G, right, using group multiplication. All right, he's, again, a little bit vague. He leaves a little bit to the imagination. You guys to tell me, how do we... how do we let H act by group multiplication? So what I have to do, right, is I have to take H in H, right, and let's say X in G. And how should I define H star X? This is slightly confusing, right? Because here H is playing the role G does in the definition, right? And S in this case is equal to G, all right? Just to be, I know you guys are getting used to this idea, so let me just put that down here. You know, S in this context, quote unquote, is G, and the G, quote unquote, is H here. Oh, HX. Yeah, I think you got it. Let's see here. If we look at E star X, what do we get? We get EX, right, which is equal to X, so there's 2. I'm sorry, I just feel like condition 2 should be condition 1. You know, I don't know. I've been looking at 3 books on this topic, and they all are a little bit different. And I think he's a little bit odd in putting the first one. I don't know, whatever. Who cares? Apparently I do. Let's see here. So on the other hand, if we look at A star B star X, right, parentheses, what is this? This is A star BX, which is, by the way, A times BX. But by associativity of the group multiplication, that's equal to AB times X, which, by the way, is AB star X, right? For all A, B, and H, and for all X in the group. So the group multiplication by a particular subgroup naturally defines also a group action on the total group. Okay. Of course, you could take the case that the H was equal to G, and this would also define a group action, right? So a group acts on itself by its own multiplication as well. You know, there's that. All right. Example 3. A little bit more, well, I don't know if it's more exciting. It's an example, though. Let G equal to the non-zero elements of a field. So this is basically a field minus 0. All right. Remove 0 from the field. Then you have the multiplicative group in the field. For example, non-zero real numbers, non-zero complex numbers, non-zero rational numbers, the non-zero elements of Z mod a prime. All of these things would be examples of this. So if you have V, a vector space over F, all right, then the scalar multiplication defines an action of G on V. So if I do C star V equals to CV, where this is the scalar multiplication in the vector space. Of course, we have 1 times V is equal to V, and we also have that if we have AB scalar multiplied, right, that's equal to A. So scalar multiplication in a vector space, essentially by definition, is a group action with respect to the non-zero. It's a little bit more than that, right? Because the scalar multiplication also has something to do with 0, if you remember the full story from linear. But anyway, if we look at the non-zero scalars, scalar multiplication is a group action on the vectors. Another example. If you have V a vector space over F, all right? I like this example more. This one's more fun. And and we're going to be more specific, V equals to Fn. In other words, the n vectors with entries from the field, column vectors, right? The concrete set of column vectors of order n. Then, if you take any subgroup, G, a subgroup of G, L, N, F, right? Which was what? This was, remember what this is? This is A and the n by n matrices over the field such that the determinant of A is what? Not equal to 0, right? Yeah. We did define a more general sense of general linear group over something that wasn't a field, but anyway, this is how it works over a field. And anyway, so this will define a group action on the vector space. You want to guess what the group action is? So I'm going to take a matrix A times a vector V, and what's my group action going to be? We need that I group acting on V is equal to V for all V in the vector space. And we also need that if I have A times B times V, it's equal to A, B times V. What will do these two things for us? Right, you guys got it, multiplication. So we just do plain old matrix column vector multiplication defines a group action. Indeed. If you're like me, after you see these 4 examples, you start to go, what's not a group action? I mean, these are a pretty broad set of examples, I think, yeah? All right. All right, so it brings us to a proposition. Let G be a group and S a set, all right? Any group of homomorphisms all right, any group, oh, I'm sorry, and not any group of I have inserted a totally unnecessary and very destructive word in here. This of does not belong. Any group, and there's an extra S. Any group homomorphism, yeah, that's better. Any group homomorphism from G into the sim S, what's that going to be? This is actually what I call perm S. Okay, it's the permutations of S, all right? So any group homomorphism from G into the group of permutations of S defines an action of G on S. Conversely, every action of G arises in this way. All right. So let's get to it. Proof. So he says, take a homomorphism, phi, from G to the set of permutations of S, right? So assume this is a homomorphism. What do we want to do? What's the claim? If we have a group homomorphism, we say it defines an action. So how are we going to define the action? Did I already do it in my example 1? Oh, this is a homomorphism. This is not a... It seems related, though. So what did you guys say? He says, let me introduce a little bit of notation. He says, let phi of A be equal to lambda sub A. All right. And notice what we have. We have that lambda A, lambda B, which is the composition, right? Composition of these. Oh, excuse me. But this is the product of, so that would be phi A, phi B, right? Which would, by the way, be phi of AB, which would be lambda AB. I'm not sure I believe this yet. I mean, that's understood. That should be understood as composition. I mean, this is composition of permutations, and the fact that this is equal to this is that it's a homomorphism, right? But you had an idea? No? So what we're going to do is we need to define a group action of G on S, right? So A is a G. Here A is in G, right? Okay? So let's, for A in G and X in where? In S. Define A star X equals to, what should we do? I mean, there is a difference between this proposition and this example. In the example, we were dealing directly with elements of the group, so we just multiply. Oh, where was it? The group was permutations, so this is kind of funny. This one is attaching different permutations to particular group elements, so it is a slightly different animal. I need to get something back out from here, which is again what? If it's the group action of G on S, I need something in S back again. How do I get something in S back again? How about this? How about lambda A of X, right? That's an element of S again. And do we get the axioms? Well, I would argue that the E times X, right, is the, what is the identity permutation? It's just the identity map, right? What identity map sends X to what? X again, so there's 2. Associativity, if we have AB star X, well that's lambda AB of X, right? But by this stuff up here, that's lambda A, lambda B of X, right? Which more completely is really this. So again, it's it's A star, if you'll allow me to skip a step here, A star B star X. I'm out of board. But you can verify that in fact that's a group action, right? I think I mostly verified it there for you. How about the converse direction then? So that this defines a group action. So conversely, every action of G arises in this way. So conversely, so what should we do? Suppose star, right? We need to take star, which is a group action, from what? From G, how's it go? G cross S to S, right? Suppose that this is a group action. What do I need to do? Yeah, I want to construct a homomorphism, right? From G into the permutations on S. So I want to construct the phi now. I want to say phi, right, of G. I want this to be a permutation on S, right? How do you define a permutation on S? This is a function then, right? It's a function from S to S. How do you define a function from S to S? Point-wise, right? So to define this permutation, I need to tell you how it acts on X for each X and S. It's pretty much only one thing we can do here, right? So this function on X is equal to what? How can I get back an element of S using G and X? All I've got to work with here is the group action. So what you do, how about this? You guys, well, I don't know, somebody here tell me. How can I use the data I have there to create something in S? I want this to be a single valued rule too, right? I wanted to define a function. How about this? G star X. Right? It's a group action that by definition is an S again, and it's a single thing because star is a function from the Cartesian product of G and S to S once more. So that defines a function. Now the question is, does it define the right kind of function? Right? Is this a permutation? How do we find if this is a permutation or not? It has to be a bijection, right? Let's see here. So, oh man, I'm a little lost there. Let me stick with the homomorphism property. Is this a homomorphism? You know?
Wait, so since it's an element of permutations, doesn't that mean that phi of G is bijective?
Well, I'm trying to define. The thing is, I'm trying to. This is my wish. I wish that. I don't have that yet. I'm trying to construct phi to be such a thing. That's my wish. And this is my definition. So what would it, if we had, let's see what we can get here though. If we have phi of G times H, what would that be? That would be GH star X, right? And then I can use the, axiom 1 of the group action that I wrote. So this is G star H star X, right? Which would be what? That would be G star what? G star. Now H star X would be phi of H of X, right? And applying the definition of phi once more, that would be phi of G of phi of H of X. A lot of parentheses, sorry. Or in a more civilized way of writing, phi of G composed with phi of H. All of this on X. See, this is very sneaky over here in the purple. This and this are function composition. So that holds for any G and H. That proves that my proposed function is at least a homomorphism, right? But I do want that it's injective and surjective, right? I mean, I want it to be a permutation. I'm going to phone a friend. What's that? Yeah, I've already asked the audience, that's right. See what you did there. Oh yeah. It's a group, isn't it? Duh. Oh. I'm an idiot. It's going to be very underwhelming when I show you why it's a permutation. So, do you guys understand this? Are we good on the homomorphism part? Let me erase that then. So let's suppose that phi of g of x is equal to phi of g of y for some g in G and for some x and y in the set, right? To show it's one-to-one, well, you can either calculate the kernel of this thing, since we know it's a homomorphism, but I'm just going to take the one-to-one directly. It works out easier. I mean, I don't know, but potato, potato. Anyway, this is g star x equals to g star y, right? Those are elements of S on both sides, right? So why don't I just take the group action with G inverse? So act by G inverse on both sides. I'm not saying multiply by G inverse, I'm saying act by G inverse. So G inverse star G star X, parentheses, is equal to G inverse star G star Y, right? But then again, by the associativity, quote unquote, of the group action, I can rewrite that as, you know, G inverse G times X, I mean acting on X, and G inverse G acting on Y, which gives us what? E acting on X equals to E acting on Y. And you can see why we need both axioms 1 and 2 here to make this proposition go, right? I need that E acting on X is what? X and Y, right? So this again is, this is by 1, this is by definition of group inverse, and this again is by, by 2. So there you have it. It's injective. Can you guys tell me how to get surjectivity then, now that we've done this? Oh, I don't want to do that. Whew, that was close. Surjectivity. So let, what do you want? Let's let y be an S, right? And G and G, so, we want to find X in an S such that what? Such that phi G of X is equal to Y. In other words, we want to solve G star X equals to Y. So what X do you use? It's pretty obvious. Choose X equals to blank. I'll help you out. There's a star in the blank. How can I get back Y? By making a very strategic choice of X here. Yeah, you guys got it. G inverse Y. So if I do that, when I feed that into here, the G inverses cancel, and we get back Y again. So you can see that, in fact, phi of G is both injective and surjective. It's a bijection. It's a permutation. And there you have it. So again, this proposition says if you have a group and you have a set, any homomorphism from the group into the set can be reinterpreted as an action of the group on a set. So in some sense, this whole group action discussion is just a kind of different take on a homomorphism of a group into the set of permutations, all right, on a set. Okay, so important definition here. By the way, did you guys know that if you look at groups of order 1024, there are 49,487,365,422 distinct isomorphism classes? It's true. That's right. That will not be one of your homework problems. That's right. Let's see here. Oh, wait a minute. I just changed books. Sorry, we don't want to do that. Although I refuse to follow his notation entirely, I'm going to go over here. So, yeah, more definitions. These are important. If you have G acting on set S, G group obviously, then the orbit of X is equal to S in the set, such that S is equal to A times X for what? For some A, and I'm going to use G. I hate using A for the group element. It's stupid. So for some G in G. He uses A for the group element here. It's dumb. Sorry. It's fine. It's fine. It's a great book. All right. See here. Then so this is again the orbit of X under G. What I'm about to write is called the stabilizer This is the stabilizer of X under G. So here we have G sub little x equals to G and G, such that G acting on X gives you back X again. All right. And then there's one other thing we sometimes like to talk about. I'm not 100%. I'm not sure about this notation, but this is what I'm going to write for now. So X in S such that G star X is equal to X for all G and G. So this is called the subset of S fixed by G. All right. The orbit and stabilizer, I think, are, important. Probably the most important to the discussion here. How many minutes do I have left? I forgot my stupid phone. Am I 8 minutes? Does that include my extra 2 minutes, or is that an actual 8 minutes?
No, that's including it.
That's including the bonus minutes? Okay. Thank you. So the other name for come on. I wrote myself a note. Some people like to call the stabilizer of X under G. For example, Fraley calls it the isotropy subgroup of X. Stabilizer is also known as the isotropy subgroup of X, or isotropy if you like. This is in fact, we can prove this, a subgroup of G. And so this is the isotropy subgroup of G. All right. So for different group actions, it's interesting to look at the orbits and the stabilizers for the group action. All right. Let's see here if we can do it. This one's a little bit too esoteric. Let's try it for this one though. Example 2. what are the orbits? What are the stabilizers? For example, 2. Let's see here. So if I ask you, what is the orbit of x? What would that be? Let's write it out. We'd be looking. So the orbit. You notice the distinction between the orbit and the isotropy subgroup. The isotropy subgroup, or the stabilizer, if you like, subset of the group. In contrast, the orbit is in fact a subset of the set. All right. So they're in different places, but they're related. So here, what was our set? Our set was G, right? So we're looking for, let's say, S in G, such that what? Such that S is equal to what? S is equal to G, so I guess we'd say H star what? Star S. Oh, X, right? I'm an idiot. Wait a minute. I'm sorry, I can't. I should have brought my glasses, sadly, truthfully. X, right? All right. And this is where H is what? H, right? All right, let me write that. But this is not just, this is what? This is S and G, such that what? Such that S is equal to what? HX, right? Do you guys remember what this is? It's things in the group of the form H times X, where H is from a subgroup. What's this? Left coset. Votes for left coset. Votes for right coset. Oh, man. Really? Oh, you guys are killing me. That's the right coset. Right? I mean, correct? Look, it's multiples on the left by the group, which makes it the right coset. Yeah, sorry, but true. So the orbits of this action are right cosets. All right? What are the what's the stabilizer? What's the stabilizer? What's the stabilizer of H here? Of X under H. So let's see here. We're looking for H and H, right? Such that what? Hx is equal to X, right? Yeah. What is it you said? Yeah, I think it's just E, right? Now, what do you know about right cosets? What do you know about right cosets? What can you say about them as they relate to the group? What's that? The order of them divides the order of the group. I think that's true. The index is the number of cosets, right? Yeah. And so it's kind of a corollary to Lagrange's theorem, right? Now, this stabilizer doesn't have to be a normal subgroup, all right? But it is a subgroup, so you can look at the cosets of it. But anyway, long story short, what we're going to find is that the orbits give you a partition of the set, all right? And then there's something called the orbit stabilizer theorem, which is going to connect the size of the orbits to the size of the stabilizer to the size of the group. and it's going to allow us to solve interesting counting problems. Anyway, we didn't get to that today, but it's a good start. So I think we're out of time. Yep.
So like, why have a state does it? It always appears like it's like